A recently published study has brought renewed attention to the interstellar object known as 3I/Atlas, presenting a collection of unusual observations that have led scientists to question its true nature and origin. As reported by News.az, citing Incal, the object has demonstrated a combination of physical and dynamical characteristics that do not fit neatly into existing categories of known comets or interstellar visitors. Since its detection, 3I/Atlas has become the subject of intense scrutiny within the astrophysics community, with researchers carefully documenting every anomaly in an effort to understand whether it represents an extreme outlier of natural cosmic processes or something fundamentally different from anything previously observed. As 3I/Atlas passed through the inner solar system, its trajectory immediately raised questions. Unlike typical comets, which tend to follow predictable orbital paths shaped by gravitational interactions and outgassing behavior, this object exhibited a series of deviations that challenged standard models. Detailed analyses of its motion showed that its path did not align with expectations for a conventional comet originating from the Oort cloud or Kuiper belt, nor did it behave like previously identified interstellar objects such as 1I/Oumuamua or 2I/Borisov. Harvard astrophysicist Avi Loeb, who has been closely involved in examining interstellar phenomena, highlighted that these deviations were not isolated quirks, but part of a broader pattern that warrants deeper investigation. One of the most striking aspects of 3I/Atlas is the timing and geometry of its arrival. Its trajectory brought it within tens of millions of kilometers of Mars, Venus, and Jupiter, a configuration that is statistically rare. At the same time, its perihelion passage, when it was closest to the Sun, coincided with a period during which it was effectively unobservable from Earth. This unfortunate alignment limited direct ground-based observations at a critical moment, forcing scientists to rely more heavily on indirect data, space-based instruments, and post-perihelion measurements. While observational gaps are not uncommon in astronomy, the coincidence of such close planetary approaches combined with limited Earth visibility added another layer of intrigue to the object's passage. The interaction between 3I/Atlas and Jupiter has been of particular interest. During its 2026 encounter, its closest approach to the gas giant appears to differ significantly from what models predict for a typical comet of its presumed type. Jupiter's immense gravitational influence often acts as a natural filter, altering or capturing comets and shaping their subsequent trajectories. However, preliminary calculations suggest that 3I/Atlas's response to Jupiter's gravity may not conform to expectations, implying either an unusual mass distribution, atypical structural properties, or non-gravitational forces at play. Each of these possibilities carries profound implications for how scientists understand small bodies traveling between star systems. The estimated mass of 3I/Atlas further complicates the picture. Observations indicate that its core is roughly 1,000,000 times more massive than that of 1I/Oumuamua and about 1,000 times more massive than 2I/Borisov. Such a substantial mass is unprecedented among known interstellar objects detected within our solar system. Despite this enormous size, the object is also moving faster than both of its interstellar predecessors, a combination that is difficult to reconcile with current theories of how such bodies are ejected from their parent star systems and survive long journeys through interstellar space. Astronomer Jason Wright, writing on his Asteroid blog, emphasized that the combination of extreme mass and high velocity places 3I/Atlas well outside the norm, even among the already rare population of interstellar visitors. Equally puzzling is the object's physical behavior, particularly its jet activity. During observations conducted in July, August, and November of 2025, scientists detected a jet pointing toward the Sun, sometimes referred to as an anti-tail. In standard cometary physics, jets and tails generally stream away from the Sun, driven by solar radiation pressure and the sublimation of volatile materials. A sunward-pointing jet suggests a far more complex mechanism, potentially involving unusual surface properties, internal pressure dynamics, or localized outgassing from specific regions of the nucleus. This phenomenon was not a fleeting or ambiguous detection. It was independently confirmed using high-resolution, high-rise images obtained while the object was near Mars, lending significant credibility to the observations. The chemical composition of the gas cloud surrounding 3I/Atlas presents yet another anomaly. Spectroscopic analyses reveal an unusually high abundance of nickel relative to iron, as well as an elevated ratio of nickel to cyanide. This chemical signature stands in stark contrast to the thousands of comets observed to date, including the interstellar comet 2I/Borisov, which displayed a composition broadly consistent with known cometary populations. Nickel is not unheard of in cometary material, but its dominance in the observed ratios challenges existing models of comet formation and differentiation. Such a composition could imply an origin in an environment with markedly different conditions from those that produced the comets familiar to astronomers, or it could point to processes that have altered the object's surface and subsurface layers during its interstellar journey. The object's trajectory adds further complexity. 3I/Atlas follows a retrograde path, meaning it moves in the opposite direction to the planet's orbits around the Sun. While retrograde comets are known, what makes this case remarkable is the object's alignment. Its trajectory remains within approximately 5 degrees of the ecliptic plane, the flat, disc-like region in which most planetary orbits lie. For an interstellar object arriving from a random direction in space, such close alignment is statistically unlikely. This precise orientation has been confirmed through multiple datasets, including JPL Horizons calculations, reinforcing the idea that the object's path is not easily explained by chance alone. Polarization measurements provide yet another piece of the puzzle. Observations indicate that 3I/Atlas exhibits an exceptionally negative degree of polarization, a property that reflects how light scatters off the object's surface and surrounding dust. Such extreme polarization values have never been recorded for an interstellar comet before, including 2I/Borisov, and are rare even among solar system comets. Polarization is closely tied to the size, structure, and composition of dust particles, suggesting that the material surrounding 3I/Atlas may be fundamentally different from that of other known small bodies. These measurements have been published in peer-reviewed analyses of interstellar objects and comet surveys, lending further weight to their significance. Taken individually, some of these anomalies might be dismissed as rare but natural variations within a broad population of cosmic objects. However, what has captured the attention of scientists is the sheer number of unusual traits exhibited by 3I/Atlas simultaneously. From its mass and speed to its chemical composition, jet orientation, polarization properties, and orbital alignment, the object deviates from expectations in multiple, independent ways. Statistical analyses suggest that encountering a single comet with one or two of these characteristics would already be uncommon. Finding all of them in one object is extraordinarily rare. As a result, researchers have adopted a cautious but open-minded approach. Every deviation has been meticulously recorded, with PrimeTimer compiling a clear and organized record of the object's distinctive features exactly as they were observed. This careful documentation reflects a broader scientific effort to avoid premature conclusions while ensuring that no detail is overlooked. While some hypotheses explore the possibility that 3I/Atlas represents an extreme end member of natural astrophysical processes, others argue that its properties may require new theoretical frameworks or revisions to existing models of interstellar object formation and evolution. Despite the speculation surrounding its nature, scientists emphasize that the current debate is grounded in data rather than conjecture. The anomalies associated with 3I/Atlas are real, measurable, and supported by multiple independent observations. What remains uncertain is how best to interpret them. Whether the object ultimately proves to be a previously unknown type of comet, a fragment of a disrupted planetary body from another star system, or something even more exotic, its passage through our solar system has already expanded the boundaries of what astronomers consider possible. In this sense, 3I/Atlas serves as a powerful reminder of how limited our understanding of the cosmos still is. Each new interstellar visitor offers a rare opportunity to study material formed around distant stars, carrying with it clues about environments far beyond our own solar system. The statistically rare deviations displayed by 3I/Atlas suggest that the diversity of such objects may be far greater than previously assumed. As more data are analyzed and future interstellar objects are detected, scientists hope to place this enigmatic visitor into a clearer context. Until then, 3I/Atlas remains one of the most intriguing and challenging cosmic discoveries of recent years, prompting astronomers to rethink long-held assumptions about comets, interstellar travel, and the variety of objects that wander through the vastness of space.